Hello and welcome to College Physics 1, Lecture 18, Friction and Drag. In previous lectures, we've gone over Newton's second law and how to apply it to solve complicated problems, and in our most recent lecture, we started to revisit each of our individual forces just to kind of get a closer look at them and develop some equations based on them. So in the last lecture, we looked at weight, apparent weight, and normal force. So we're going to continue on and this time look at friction and drag, our resisting forces. So let's just revisit these with definitions to start with. We know that static friction, or Fs, is a force that a surface is going to exert on an object, in this case to keep it from moving. In other words, we say it kind of keeps an object quote-unquote stuck on a surface. Now, this is a resisting force, so if you're trying to push an object to the right, static friction is holding the object back to the left. So we say that its direction is always opposite that of the direction that it would move if there was no friction at all. So if there wasn't friction, you'd be pushing the object to the right, so it's holding it to the left. So to start out this discussion, consider someone pushing a box that doesn't move, so some large box or crate. Well, since it's at rest, recall from our previous definitions, we know that this object is in static equilibrium. Static meaning it's not moving, and equilibrium meaning the forces are all balanced. No one force is winning the fight here. So as a result, because it's in static equilibrium and all the forces must be balanced, whatever you're pushing with, or whatever force you're pushing with, has to be balanced by an equal friction force holding it back. Otherwise, we'd see an acceleration of the object. More interesting than this even is what happens when you continue this. So say you start to push harder and harder on the box. Well, it's not moving still, so if you're pushing harder and harder, then friction has to be resisting more and more as you push harder. But, probably from experience, you know that you can eventually make an object move. So if you apply a great enough force or push hard enough on that box, eventually it will start to slip and slide across the surface. So what we're seeing is static friction basically adjusting itself so that it's always balancing the pushing force. But it has a limit. And so this maximum possible magnitude of the static friction force is given by the equation Fs max is equal to mu s times n, the normal force. So this brings in a new term. Mu s is what we call the coefficient of static friction. Now keep in mind, a coefficient in mathematics means it's just a number, so there's no unit associated with this. It's a number that depends on the materials from which the objects are made, that being the surface and the object that you're pushing. The higher the value of mu, essentially the greater the stickiness of the surface. In other words, the harder it would be to move something. Now these coefficients are often either given to you directly in a problem, or as you can see on the bottom right, some common values are also given in a table that you might need to reference if a problem tells you, maybe it's a car with, the rubber tires on concrete, then you'd reference the first values here. So this equation is a way to understand how strong your friction force is. And we'll talk about why it's based on the normal force in just a minute. Well, now we're talking about an object that is sliding, right? Because you push hard enough, it'll slip and start to move. Well, in that case, we no longer have static friction, which holds things in place. We have kinetic friction, or Fk, that is the friction force of motion. Much like static friction, this is still a resisting force, and so the direction of this new friction is always opposite the direction of motion. So in the case of a person pushing a box to the right, friction holds it back or slows it down or resists to the left. It doesn't necessarily have to slow it down, it could be balanced. The good news is, even though kinetic friction also has its own equation, it is the exact same form of the static friction equation. F is equal to mu times n, in this case with subscript k's to denote the kinetic friction. Just like mu s, mu k is just a number, and these numbers typically range from 0 to 1, and again, the higher the number, the stickier the surfaces between the two. Something interesting to note about this expression, though, is that it's based on mu and n. Now, technically, n is related to the weight because the normal force pointing up should balance the weight pulling down. So, in a sense, this is dependent on the weight of the object. But notice there's nothing about velocity, for example, in this equation. It's a common mistake that people tend to believe that how fast the object is moving will play a role, but it does not. So this isn't really a slide that I have students take notes on, but I just think it's interesting. So even though you might be touching a surface and it feels smooth to your hand, at a more microscopic scale, it's certainly not smooth. In fact, almost any surface is rough when you look that close. So when two objects are in contact, they don't make a perfectly smooth fit between the two. Rather, you have jaggedy surfaces where there's like high points and low points, and they basically just lock into each other. One of these high points can get stuck into the dip of the other surface, and they're stuck. And so you have to push against these objects hard enough to overcome the forces that are holding these contact points in place. Now, this amount of contact depends on how hard the surfaces are pushed together. So that's why it depends on the normal force. Right? The normal force, if you push really hard against the surface, well, then the normal force is pushing back just as hard. And the point is, you have to kind of take that into account when looking at friction. So to begin this discussion, to continue this discussion, let's just work out an example. This is a fairly basic one, but it does apply a couple different equations in one. So I tend to like this question quite a bit. In this case, we have Carol, who is trying to move she's trying to move her 32 kilogram sofa to a different room. So she's placing sofa sliders. I've often heard these called moving men. These are just little discs that you place under the legs of furniture so that they're easy to remove. So we're told that the coefficient of kinetic friction is 0.08. And she then pushes the sofa, once these are underneath, at a steady speed of 0.4 meters per second. The question asks us, how much force does she apply to the sofa? So let's start like we always do. Let's consider what forces we have. Well, there's friction holding it back because she's pushing on it forward. Every object at the Earth's surface has a weight, and because it's on a surface, the surface pushes back with a normal force. Altogether, we'll get a free body diagram that looks like the following. A weight pointing down, the normal force pointing straight off the surface, in this case vertically, her push, F, that we'll call it, to the right, and the kinetic friction force holding it back to the left. Because she is pushing at a steady speed, our forces are balanced. Right? There's no acceleration, so there should be no net force, which means no force is really winning the fight here. So with this in mind, let's go ahead and write out our Newton's second law, a common process that we do throughout all of these problems. Right? You draw a free body diagram and write out Newton's laws for all of these. In the x direction, we have her pushing force F to the right and the friction force of kinetic friction to the left. There is no acceleration, so this is set equal to 0 instead of ma. Now in the y direction, we have the normal force pointing upward and the weight pointing downward, making it negative. And again, there's no acceleration, especially in the vertical direction, and so the equation is set equal to 0. Now, at this point, we have to think about what the question is asking us. It says, how much force does she apply to the sofa? In other words, it's looking for that value of F, capital F that is. Well, from the y equation, from the x equation, we see that force F. F is equal to, if we add friction to the other side, the kinetic friction force. This is the only place that F shows up, so we know we have to use this equation to solve. Now, unfortunately, it's not this simple because we don't know what the friction force Fk is. But we are given mu k, the coefficient of kinetic friction. So that's almost like a hint that you want to expand this equation. Remember that friction is equal to mu times n. Now, we do know what the mu value is, the coefficient of friction, but we still don't know what the normal force is. So sometimes this can be a troubling point for students. We need to know what the normal force is in order to solve for the force F. We don't know it, it's not given to us in the problem, but from our y equation, we can see that the normal force is equal to the weight, right? If you add the weight to the other side. Well, that's sort of helpful, but we still don't know the weight of the person either, or excuse me, of the sofa either. We are given the mass. So in order to switch between weight and mass, we know that weight is equal to mg. Thankfully, finally, we do have the appropriate values. We know the mass is 32 kilograms, and we know g, as always, is 9.8 meters per second squared. Plugging this in, we find that the normal force is equal to, actually didn't write this out, it should be just under 32, or under 320, because this is 32 times 9.8. And so what you get is 313.6. We'll say 314. So we have 314 newtons for the normal force N. Well, now we can take this and plug it in to our equation above. We know it's mu times N. Mu was given in the problem as 0.08. And we just found what the normal force is. It's 314 newtons. So once you plug this in, you'll get a value, I think with some rounding, equal to 25 newtons. That is the force F that she pushes with. So this isn't a long problem, but it can be confusing for students because we are using multiple equations in one to solve. Right? We started with the x equation, F equals Fk. But then we realized, well, we need to break this into mu times n. Then we realized we didn't have n, so we went to our y equation and said n is equal to the weight. But because we didn't have the weight, we had to break that into mass times gravity. And then we were able to plug all that in together and solve. So just be careful. A lot of times if it seems like you don't, when we started, we didn't know what the friction force was, think about equations that can be split up. F is equal to mu n, weight is mg. That kind of stuff becomes a lot more relevant in these problems moving forward. This brings us now to the other type of resisting force. We've been ignoring this one the entire time throughout our discussions thus far. This is the effect of air resistance, drag, given by capital D. Again, it's an opposing force, so it's going to oppose the motion of an object, in this case, one that is moving through a fluid. Something that flows, so that could be air or water, for example. Now, drag has a very unique equation, at least compared to other ones we have in this course. The equation for drag for an object moving at a speed v is 1/2 CD rho AV squared. Now, there's a lot of stuff here, so let's talk about what each of these are. We already know that v is the speed. Well, rho is the density of the fluid, so like how many kilograms for every cubic meter. A is the cross-section area of the object. So when we say cross-section, we mean just imagine like slicing straight through the object. That is the cross-section area, the area of that surface that you've basically sliced through. And then CD is what we call the drag coefficient. This is a number that depends on the shape of the object. More aerodynamic objects have a smaller value of CD, while objects that are not very aerodynamic have a large value of CD. Now, I do not make students memorize CD values or density values or anything like that. On the right, you can see a chart of various CD values on the top and density values in the bottom. So note, for example, the commercial airliner has a very, very low CD value, and that makes sense because we want objects to be aerodynamic, in other words, have low CD values. So in the case of an airplane, you certainly want it to be aerodynamic. But a running person has a CD value of like 1.2. I mean, our body, our full front of our body pushing into the air is not very aerodynamic. In terms of the densities, at least in our case, we're not really going to work with situations where we're moving through things like olive oil or honey. For the most part, you'll just want to focus on the density of air at sea level, which is approximately 1.2 kilograms for every meter cubed. Now, a really cool and fascinating result of all of this is the concept of terminal speed. You've probably heard of this before or heard of it as terminal velocity. Looking at the equation that we just had for drag, realize that it's heavily dependent on speed, right? V squared. So if I were to say double the speed, well, that 2 gets squared to 4. So we're actually quadrupling our drag force. Or if I increase my speed by a factor of 4, 4 squared is 16, so our drag is increased by a factor of 16. So drag is heavily dependent on speed. As the speed increases, so does the drag force. This will keep happening. In other words, the drag force will keep growing in size until it reaches a situation where its force balances the force of whatever is pushing or pulling on it. In many cases, we'd be looking at an object that is falling through the air, like this basketball you see here. It has, initially, when you first let go of it, a big weight force, but only a tiny little drag force because you've only just let go of it. It's moving at a slow speed. But as it picks up speed, its drag force rapidly increases. And that continues until it balances the force that's pulling it down, in this case, weight. Well, once your forces are balanced, neither one is winning a tug-of-war match here, so they're equal and opposite, which means you're not going to get an acceleration in either direction, which means you stop picking up speed or stop accelerating. At this point, the object is said to have reached terminal speed. It's the speed at which the object can no longer travel any faster. So, to practice all of this, let's do another example. This is going to be a little bit of a longer one just because we have to deal with 2 objects, but still. In this problem, we are given that a 75 kilogram skydiver and his 0.02 kilogram pet mouse, because why not, are falling after jumping from a plane. The problem tells us to find the terminal speed of each. Now notice that we are given the dimensions of the objects in the image on the right, so that's going to help us calculate our area. But we do have to be careful about what our rho value is and what our CD value is. Keep in mind on the last slide, 2 slides ago, that a running person has a CD value of 1.2. Well, a person running through air is basically identical in terms of the drag that would be experienced to a person laying flat and falling down like you saw with the skydiver. So we're going to assume that it has a CD value of 1.2, which is the CD value for roughly a cylinder. And I mean, if you think about it, our bodies are roughly cylindrical. We have kind of a curved exterior and a long, height. So we use a CD value of 1.2, and because we're assuming it's moving through air, we get a density of 1.2 kilograms per meter cubed. That's supposed to say kilograms. And so, once we have those 2 values down, all we have to do is worry about finding our area before we start solving the problem. So I'm going to use capital M for the man, which is probably going to get confusing, and lowercase m for the mouse. The man, as you see from the photo, has an area of 1.8 times 0.4. This gives you an area of 0.72 meters squared. Now the mouse has an area of 3 by 7 centimeters, in other words, 0.03 times 0.07 meters. 0.07 meters. Multiplying this out, we get an area of 0.0021 meters squared. With the areas known, let's go ahead and start working out our problem. We'll start with a free body diagram as always. Now, in this case, we do have a couple forces. We have the weight of the person or mouse pulling them downward, hence why they accelerate down toward the earth. And there's a drag force pulling up. Now, this is a point of technicality. Remember what terminal speed means. This problem asks us to solve for terminal speed, which is a hint that it's important here. Remember that terminal speed occurs when your forces are balanced. So you want to draw your forces the same length. This is the drag force. So let me label axes, X and Y. Okay, well, let's write out Newton's laws and see what happens. So we have the sum of forces, Fx, and the sum of forces in the y direction, Fy. Well, in this context, there are 0 forces in the x direction. So when we try to add them up, there's nothing there, so it's equal to 0. Zeros are a friend in physics. Now, in the y direction, we do have forces. We have the upward drag force and the downward weight force. In this case, be careful. Students mistakenly do this almost every semester. We're at terminal speed, which is when the forces are balanced. In other words, no force is winning against the other, so we don't see any acceleration at all. In other words, we can also set this equal to 0. Okay, well, the problem asks for terminal speed. There is no speed in this equation as we have it. But let's kind of put this all together. If we rearrange this, we have drag equal to weight. Well, we can expand on this even further because we know what each of these equations are. Weight is equal to mg. Drag is equal to 1/2 CD rho AV squared. Right, so that just came from drag, that just came from weight. Well, now we see a speed, v, that we could solve for. So let's take this over and do that. We have to do some basic rearranging here. I'm going to multiply both sides by 2 to get rid of the 1/2. Then divide by CD rho A. Once I do that, you can take the square root. This is going to give us a speed v of the following. The square root of 2mg divided by CD rho A. This is our equation for terminal velocity. Now, the downside to doing this problem is that we have to do it twice. We don't have to set everything up again, but we do need to solve it twice because there is 2 objects, a man and a mouse. So let's start, let's say, for the man. We have the square root of 2 times the mass of the man, which was given to us as 75 kilograms. And we know the acceleration due to gravity is 9.8 meters per second squared. All of this gets divided by CD rho A. CD is just a number, 1.2, times rho, which is 1.2 kilograms per meter cubed, and the cross-section area of the man, which was, in this case, 0.72 meters squared. Okay, so all of this is underneath our square root. Hopefully we plug this into our calculators appropriately, and we would get an answer for the terminal speed of the man to be about 38 meters per second. Okay, that's technically one of our answers. Now we just do it again for the mouse. In this case, the only thing that's changing is the weight and the area. All the other numbers stay the same. So we're left with 2 times the mass, which is 0.02 kilograms, times the acceleration due to gravity, which is 9.8 meters per second squared, last I checked. All of this divided by the 1.2 drag coefficient, the 1.2 density, kilograms per meter cubed, and the area of the mouse, which was 0.0021 meters squared. This should get you an answer of about 11 meters per second. Now realize that this is a much lower value than the terminal speed of the man, which is part of the reason why a small animal like a mouse can survive a fall from a great height. That's because their maximum speed that they're going to fall at is 11 meters per second. We fall at almost 4 times that rate. So this is a really interesting problem that segues us a little bit into animals in nature. Looking at the equation that we just wrote to solve the last problem, you should be able to see that it depends on m over a, or mass over area. I highlighted here in the equation that we had. Mass divided by area. Well, small animals have very small ratios of this value of m to a. And so if that's really small inside of here, then they're going to get a really small velocity. And so the mouse that we were talking about, it gets its small value, or it has its small value of m over a. And so it can fall from great heights and still survive. Now, some animals can also reduce their terminal speed even further, right? By increasing their area. In other words, increasing the amount of drag that they would experience. And so that's typically what you're seeing when a frog jumps, it spreads its legs all the way out, or even a cat does it sometimes. You're seeing the animal using the concept of terminal speed and drag, but without, presumably, knowing anything about the physics behind it. So I just think that's fascinating. All right, this brings us into our 3 questions to close out this lecture. Question number 1 says a box on a rough surface is pulled by a horizontal rope with a tension T. The question asks, the box is not moving. It asks in the situation, which is true, if the box is not moving. Okay, well, if it's not moving, but it's being pulled at, that means there must be a balance of forces. Friction is still holding this object back in place, right? Because you're tugging on it. If there was no friction, then this would certainly move along with you. But you're just not pulling it hard enough. Friction is holding it in place. Oops. And so what we see is that they should be equal to one another. The answer is B here. The amount of friction pulling back is going to balance the tension force pulling it forward. I should have drawn it the same length. I just got lazy. So they're the same size. Now, keeping this in mind, let's go to question 2. Here we see a similar situation, a box with 100 newtons as its weight that is pulled down by a 30 newton horizontal force. Or pulled by a 30 newton horizontal force. Question asks, does the box move? Okay. Well, the box would move if your force of 30 newtons is greater than the friction force. So let's just go ahead and try to solve for the force of friction. First of all, recognize, just real quick, a free body diagram. You're going to have the weight down. It's on a surface, so the normal force upward. It is being pushed or pulled by a rope. Does it say by rope? It just says it's pulled. So we'll just call this some pulling force F. And then you have the friction holding it back. So it asks, does the box move? Well, think about that. We're basically just wondering, how big is that friction force of Fs? We know that it's equal to mu times n. Well, mu, S, is given to us in the picture as 0.4. And then the normal force N, well, N is related to the weight, so we have the sum of forces in the y direction here, N minus W. So N is equal to the weight, and this allows us to plug in our values. So we have the normal force times the weight, which is given to us as 100 newtons. So this will give us a value of about 40 newtons for static friction. So that means it's pulling back with a force of 40 newtons. So that gives you your answer. The static friction is still winning the battle here. It's bigger. And so, no, it will not move if this is the case. And on to our, I believe, last question. A box is being pulled to the right over a rough surface. Tension is greater than the friction force this time, so that the box is speeding up. Suddenly, the rope breaks. What happens? The box blank. All right, so this one tends to trick people. It's not going to instantly stop. I mean, there's some forward momentum that's going to carry that thing forward, so no. It'll continue with a constant speed that it had when the rope broke. Some people choose this, but remember, in this case, we are taking friction into account. So with friction being taken into account, it will certainly start to slow down as soon as the force being applied disappears. It could continue speeding up for a while, then slow down. Well, that's certainly not true because there's nothing there to push this thing faster, right? It's just being slowed down now. It says it keeps its speed for a short while, then slows and stops. It does not keep its speed for a short while, as we just discussed. It is variable and always changing. So this brings us then to the final option. It slows steadily until it stops. And this is certainly true. This is true of, I mean, let's say an air hockey puck. You hit it across the table. It's eventually going to come to a stop, or, anything like this. So just be careful with how some of these are set up. In this case, again, it will just slow to a stop. Don't trick that with, or confuse that with the idea that it has to stay at like some constant speed for a while. So just be careful. Anyways, that's it for this lecture. In our next lecture, we're going to take a look at kind of our final section here where we take a look at interacting objects, so objects that are physically contacted with by one another or connected by a rope. And then we'll look at some ropes and pulleys as well. As always, thanks for watching and have a great day.